Like Shivani said, my name is Andrew. I'm going to be talking today about different types of data science modeling, either everything more from frequentist to Bayesian modeling. You probably have heard some of these or seen some of these kind of practices, even if you haven't heard those terms or referred to them differently. So the goal of the workshop is pretty simple. We're just going to use some familiar tools with different probabilistic methods, and using some examples along the way to try and find ways that are, be fast, get a good fast baseline for whatever kind of data you're working with, just so you know where your starting point is before you get into more complex models. And we're going to use the Bayesian data modeling to kind of see where the uncertainty in your data might be. And it's not. There it is, okay. So, I'm going to drop this back into the code. This is the, I'm going to drop this back into the chat just in case everyone can't see it. Let's see. There we go. So this is the link to the Google Colab. That's what we're going to be using for the demo. So we're going to start with this easy frequentist model originally, then we're going to scale it up by adding in some random forest. And then we're going to go through the same kind of thing. We'll start with a simple Bayesian idea and then add in more things to see where the uncertainty in the data came from. As we go along, I'll just check to make sure if there's any kind of issues. Everyone here got the Google Colab? Okay.
It's https://go.hawaii.edu and then /EBD. We'll just make that here. Can you push us right? Yeah.
Everyone get it, or their work or not?
Yeah, sure.
Yeah. Shivani, I think he needs to be added into the Zoom.
I just need to be added to the Zoom.
It's that thing right here.
No, he's not in this. It's open with. We used Google Colab before.
Yeah, I have. Just.
So just open it any particular app.
Yeah, open with Google Colab.
Yeah, I went with Google Colab because some of the Bayesian libraries didn't play nicely with Jupyter Notebooks, and I didn't have everyone to change the settings and all that kind of stuff, and Colab had everything working natively, so sorry if that was the intent behind it. Well, everyone's catching up with that. We'll talk about the basic idea of the difference between frequentist and Bayesian modeling. So, again, I like sports and statistics, so imagine a baseball player has over 3 years, he gets 1,000 at bats, and he hits on average 25%, 250, which is a pretty average baseball player. Year 4 comes around, starts off the season, and hits 25 out of 50, which is 500, which is like be a record-setting kind of case. So if you just look at that, is that really a good way to judge him? If you look at just on a frequentist method for that year of data, it would say that he's a good hitter. If you wanted to add some uncertainty onto it, if you look at his past data, and you're not necessarily using that to weigh his current year, you can add some prior beliefs about a different hypothesis. That's more of how you can use a Bayesian idea of thinking to not use old data on the new season, but use some of the experience for your hypothesis and whatever you might be doing. That's kind of one of the ways that I like to think of it. So it's a lot of times frequentist is what is the single best estimate, and then Bayesian is more what values are plausible given what we know before and what we've just seen. So frequentist modeling usually assumes that there's one true value for each parameter, even if we don't know what it is yet. And the model's job is to estimate that value using data. So most of us have already seen these kind of models, even if they aren't always referred to as frequentist. The key idea is that the model returns one best estimate rather than a large range of possible answers. So this is often why these methods are fast and widely used in practical data science. So we're going to use Scikit-learn. It's easy to use. It stays almost identical across whatever algorithm you're actually trying to do. You always just prepare your data, choose your model, fit, predict, evaluate. It's really simple once you know how to do it. You can often just use the same kind of formula and just make some small changes. So we'll use this approach to build a starting baseline model so we have something to compare other things across it. As long as we know the pipeline, like I said, it's easy to do, and then we'll just use the same kind of pre-processed data for the Bayesian models afterwards. So for this first data set, we're going to use the Titanic data set. It's an easy data set that's easy to understand. It's got features and the goal is going to be to predict whether passengers survived based on characteristics like what class they were on the ship, first, second, third class, their age, their sex, if male or female. And since this is a classification problem, the output is category instead of continuous. So we'll basically just be modeling it into the binary outcome of survival or death. So the reason why you want to look at multiple things is if you just looked at their survival rate by passenger class, you'd get something like this, which is good if that was your only data point, but as we know, there was a lot of other data to consider. Like I said, how old they were, whether they're man or woman. So that's why you often want to use all the different features combined to get a better idea of whether or not they survived. So let's see. Let's switch to the notebook. So let's see. Right here, this is the. Is anyone not on the Colab yet? All right, so if you hit run all, that's fine. I'll still just go through it. If not, we'll just do it cell by cell. So this is the import. It just pulls in all the stuff. This is the data set. You can see the different types of categories, whether for the passengers, they survived, their class, sex, age. This is where they embark. Some of these things are duplicates, some of them are just binary, some of them are spelled out. But so down here, this is, like I said, this is the sample for just, if you were looking at for just one of the characteristics, you can get that. This is our pre-processing for the data, and this is where we're going to get the logistic regression, which this means that the model predicted the accuracy, whether or not the passenger lived or died 78% of the time. This isn't saying that 78% of the passengers died or lived. This is saying that the model is accurate. We got that by training it on, let's see, right here, test size 2.0. Let's see. Yeah, so that's where we got that on the amount that we tested on versus what we trained it on. Because you don't want to test and train on the same data, so this model splits it into percentages for what amount it gets trained on and what amounts gets tested on. You can always mess with this and you get a different variable. If you were to test it on the same amount, then this should change. Didn't change a lot because it's a small data set, but it went from 78.2 to 78.3. But you will see there's other things you can change as well, depending if you want to look at different kinds of, if you want to get rid of features, change features, or add features. Let's see. Okay. All right. So has everyone gotten to that part of their? So the default threshold on the way for the logistic regression is it was a 50%. That's the default thing for how Scikit-learn works. Is that it's basically the threshold of whether they lived or died is 50%. You can always could change that depending on what you were modeling. If you wanted to give it a higher threshold to get to the binary yes or no, you could do that as well. There's lots of different ways to mess with the data depending on what your goals are. But just for simplicity and consistency, we're going to keep it at the default at 0.5. So now models like logistic regression assume simple relationships between features and outcomes. Real data often contains nonlinear patterns or interactions that simple models may not miss. So random forest addresses this by combining a lot of different decision trees where each learn different patterns in the data. The important idea is that increasing model complexity does not change the overall workflow, really. You still prepare the data, fit the model, and evaluate the results using the same structure. So as models become more complex, they can capture more patterns, but they also risk memorizing noise instead of learning general rules. So you don't want to overfit the data because that means when the model performs well on training data, but poorly on new data. Random forest can improve upon logistic regression results by primarily better modeling nonlinear regression, or nonlinear relationships and complex interactions in the data, and by reducing the risk of overfitting through ensemble learning. So the goal here is to find a model that generalizes well rather than one that simply memorizes the training data. You usually want to start with a simple one like logistic regression. You don't want to immediately use random forest because there's a chance, depending on what data you actually was trained on and what you actually have, it actually might perform worse than the simpler models. That's why you usually want to have a simple model first. It's quick and it gets you an idea of when you actually go to comparison whether or not it's correct. Yeah, so let's see. So the next part is the random forest, where you use the random forest thing where it predicts the prediction and the accuracy. It actually shows that now the model predicts at 85% likely of whether or not it predicted accurately that someone lived or died by looking at nonlinear relationships. So the improved performance usually happens because the models, like I said, captures the more complex relationships. This will give us a way to see which variables the model relies on most. It also comes with a trade-off, though. As models become more powerful, they often become harder to interpret. That can lead us to thinking about uncertainty in different ways of understanding model outputs. So the models we built so far produce single best estimates. In real situations, we often care about uncertainty and confidence in the data. Like how sure are you this is accurate or not? Bayesian models treats parameters as hypotheses rather than fixed unknown numbers. So it doesn't really replace frequentist thinking. It adds another perspective. The shift is from asking what the best value is, to what is plausible given the data. So I'm gonna try and give you a Bayesian example without a lot of heavy math. So we're gonna start with a prior belief. We're gonna use tennis because that should be pretty simple. You play a tennis match. You win or you lose. So the prior belief is about a skills player, which represents what we think before seeing any new evidence. After observing wins and losses, we'll build a belief using that data, and the result is the posterior distribution, which reflects both the prior and the likelihood. So suppose you're playing tennis with a friend. Yeah, you play 3 games. You win the first one, they win the next 2. And based on that, you come up with theta, which is you come up with a hypothesis on what you think is the outcome. Theta 0.1 is that your friend is a much better player than you. You would only win 10% of the time. Theta 0.3 is that he's a better player. You probably win 30% of the time. Theta 0.5 is equal skill. Theta 0.7, you're the better player. Theta 0.9, you're the much better player. So the prior is your belief if those hypotheses are correct. So we'll start with the idea that for the prior, that all of those hypotheses, the 0.1, 0.3, 0.5, 0.7, 0.9, are all equally valid. Let's see. So right here, this is the theta. This is all your hypotheses. This is your belief on which one, how likely you think those are based on nothing. The likelihood is the result of the 3 games played, the 1 win for you, 2 wins for your friends, and the theta. And the posterior is the likelihood times the prior. So, I'm going to make this more sense in a second. Show you how this could change. So let's see. So this is it right here, in this part of your demo. So the prior, like I said, right now we're going off the idea that for the prior that all those hypotheses are equally likely. So this is your friend. You know your friend. And you know on this day that you played tennis, this is the first time you ever played tennis with him, but you know that you were sick that day. You had a cold, and they were fine. And you also know that you played tennis for 5 years in high school, and they barely play on the weekends. So your belief is that instead of that you're equal, that all these hypotheses of who's better or who's not better are all the same, you actually believe you are probably the better player and just had a bad day. So you can change the prior, which is this line of code right here. We're going to make this one active, and we'll comment that out. So now your belief, instead of, so you'll see in a second we change it. So now this 0.05, you said you think there's only a 5% chance instead of 20 that he is a much better player than you. That there's a 15% chance that he's a slightly better player than you. And you figure there's only a 30% chance you're at least equal in skill instead of 20. A 30% chance that you're better than him, and a 20% chance that you're much better than him. Because you've played a lot of tennis and you were sick that day, and they weren't. So using your prior knowledge, you can, even though the data is small, you can change that. So now let's run this new data. And you can see how it changed here. Now let's look at the graph too, how this changed when you hit the graph. So the new data, I should have probably saved it beforehand. So before, there was a 19% chance that, even with the likelihood of the prior, that he was a much better player, a 34% chance he was better than you, and a 30% chance he was equal. So now with the new version, with your new prior knowledge, you can see that it's much more likely that you're even or you're slightly better instead of him being much better. You can see that's changed. So now how can you use this for something that's not tennis? Let's say you are running some kind of experiment where you're testing water in a large area. You've got different sensors. You've got 5 different sensors in an area. And when you come back to look at your sensors, you see that 2 of them have been knocked over and damaged or covered in mud. So you know that those aren't probably as likely to give you accurate results. So instead of giving them all the same amount of weight, 20% to your data, you can modify it to where the 3 good sensors each get 30%, and the 2 damaged sensors each get 5%. Because you know that while you're not necessarily discounting that data, you're giving more weight to the data you believe is more likely to be valid. Now, you don't want to use priors recklessly all the time, because then it could always poison your data. If you decide, like, no, in this example, if you're like, I know I'm a much better data, and you gave 80% to the 0.9 theta, that would poison the data unnecessarily. We're giving it too much of your own personal bias. So usually you would want to change the prior if you actually have a reason to believe so. If you actually have prior evidence, name prior, you have prior evidence that really does tilt the data in that, especially when your data point beforehand was 3 games that you played. You're basing a lot of this on 3 games and the hypotheses you're creating. So it is kind of a balancing act a little bit. Change that too. So what changes? So both approaches are useful, both the frequentist and the Bayesian. Frequentist models are fast and they're excellent for initial modeling and quick experimentation. Bayesian models become valuable when uncertainty or decision making is important. The biggest practical difference is not in the code, but in the interpretation of the results. So the next part, we're going to be using the PyMC library, which that samples from the posterior distribution to approximate possible different parameter values. In other words, the library isn't searching for one best model. It's going to be exploring the many believable versions of the same model. So let's see. So it explores everything using the sampling. Instead of giving a single coefficient, we're going to give it a distribution of plausible values. Let's see. Did I not put in my picture? Okay. Okay. So this is, we're going to talk about different credible intervals and uncertainty directly. You'll see that the Bayesian models provide more information, but also require more computation time. So let's see. We're going to go down. And to make sure that you have in the library for that. Let's see. That's pre-processing. And here's our model. So this is not a lot of data, but it still takes a little bit longer to actually execute. Bigger models require a lot more because it's doing burns in for the data and a lot of different sampling sizes. Until we get down to here. So this is our Bayes table. Let's see. So the mean, this is our best, the mean intercept, that's the average value of the posterior, the best overall guess. ST, that's the standard deviation. This is our 94% credibility interval, the high end and the low end for each one of these things. All these values are negative because in this model for the Titanic data, 1 means alive, 0 means dead, so that's why all the beta values are going to be 0. So a better way to actually look at this is going to be through a graph, I think, will make more sense. Let's see. Which... So then if you actually run Bayesian logistics, you get the same percentage. It's still a 78.2% logistic approximation accuracy, which, so it got to the same place, so what's really the difference? If you look down at the graph here, you run this. Let's see. Yes. All right. So I'm going to actually go back to this because I made notes to make it easier to see. Yes. So the blue curve, this shows where the model thinks that the coefficient probably lives. The mean value is the best overall estimate. The 94% highest density interval shows where that's about 2 standard deviations. It shows where there's a 95% chance that the true effect lies. Let's check this. So you can see here the age, it's about negative 0.34. Sex is negative 2.6. This is the comparison of first class versus second class at negative 0.98, and the comparison of first class versus third class is negative 0.22. So what this means is that the most individual value, the most individual statistics and points in the data that matter as far as someone lived or died is whether if you were a man and if you were in third class. So in other words, third class men were the most likely to have died according to the data, as opposed to things like whether if you were old or young had a very little impact, and if you were first or second class had some. And if you look at where the ranges are from, so the mean here is negative 2.2, and the range is from 2.7 to 1.7. So even if you look at anywhere in the range, the lowest end of the range here is 1.7, and here is 1.5. This shows that even if you go 2 standard deviations down, this still had a bigger effect than it being from first to third to first to second. And the same thing with being a man, obviously at least a 4 times greater chance than whatever age difference there might have been if you were old or young. So it wasn't necessarily women and children, it was women first. At least according to this data. So what's the takeaway? Frequentist models, they're fast and reasonable models that can give you a good reference point as a baseline. Bayesian models are helpful when we care about uncertainty or want to incorporate prior information. Frequentists answer what works best, and Bayesian answers how sure are we. The goal is not to choose one approach over another, but knowing when each is appropriate and useful. So yeah, that's about all I got, unless we wanted to talk about different modeling or different changes in the data. I'm happy to take any kind of questions or comments you might have. That's about it.
Folks are live here, unmute yourself, you can run the questions in the chat. Any questions for you? I'm not seeing any questions in the chat. If there are no questions, then I thank our speaker, Andrew. Thank you.